We know the stars sparkle at night, but what's happening inside those balls of gas? Conny Aerts uses observations and complex math to answer this question. She shares the 2022 Kavli Prize in Astrophysics with Jürgen Christensen Dalsgaard and Roger Ulrich for their work studying the pulsations of stars to learn more about their inner workings. Scientific American Custom Media, in partnership with the Kavli Prize, spoke with Conny to learn more about her contribution to this work. Conny Aerts has spent her life watching the sky.
People tell me I still do that today. When I exit a house or a building, I automatically look up.
It all started when she was a young girl. Her family lived on a remote, sandy road with no streetlights, so she had a great view of the stars.
So looking up was natural to me as a child, and I was just curious what happens inside these tiny little dots in the sky.
She dreamed of being an astronomer.
But, I come from a workers' family, so I had no connection to any cultural life or higher education, let's say.
Conny assumed that her dream was out of reach. But all of that changed after a conversation with the head of her primary school. He noticed that she was excelling at math.
And he really asked, what do you want to become later? And so I said, well, if I can choose an astronomer, but my mother wants me to become a seamstress. I don't like that at all.
The head of her school didn't like that either. So he worked with Conny on a 10-year plan. He even talked to her mother.
He said, I will convince your mother. I will tell her that you would be far better off in your future. And I'm sure I can convince her to let you go to a secondary school with a lot of mathematics in preparation of university.
The plan worked. And after lots of effort, including a 3-hour bus and bike ride to her secondary school, Conny found herself in a PhD program, studying astrophysics. By then, she'd specialized in not just any stars, but big stars.
So my PhD topic was to study stars that are more massive than the sun. Those stars, they actually rotate very fast.
To give you a sense of how fast these stars move, Conny says our sun takes about a month to make one rotation. The large stars she was studying revolved in just one day.
When a gaseous ball rotates fast, the physics and the chemistry is more complicated than in stars like the sun. And so I wanted to understand that.
As she was working on the puzzle of how these stars rotate, Conny went to her first academic conference.
I didn't understand much of all the talks. That's the way it is when you go to a first conference as a student. But there was this one talk by Professor Steve Kavli.
He was studying stars as well, but the technique he used was similar to how scientists study the deep interior of the Earth.
If we want to learn what is happening deep inside our planet, well, we can't drill a hole because we can't go deep enough. So seismologists of the Earth, they use earthquakes because earthquakes generate waves, and these waves travel inside our planet. They are the tool for the seismologists to get to the physics and the chemistry deep inside our planet.
Stars might just look like little dots in the sky, but they have their own quakes as well. When the gas in a star heats and cools, it causes the surface to pulse.
So these tiny fluctuations give a change in the brightness of the star over time. And so by measuring these brightness variations, we can deduce the frequencies of the waves that are actually happening inside the star, because it's not only the surface, it goes up and down globally, the gas.
This approach is known as asteroseismology, and the professor at Conny's conference was using it to understand the rotation of collapsed stars.
And for me, that was such an eye-opener. I thought, well, I can apply it to my massive stars if I could only have the measurements.
But this was back in the 90s, before scientists had the tools to observe star quakes in space. At the time, astroseismologists had to measure those pulses from Earth. It would take at least a decade to gather enough data to understand the waves pulsing inside a massive star. But that didn't bother Conny.
I don't mind having a plan that takes long. That doesn't scare me at all. On the contrary, I find that motivating.
So when her academic supervisor gave up on a star he'd been studying for more than 10 years, Conny kept going.
Whenever he sent me to the telescope, I secretly continued to monitor that particular star. And somehow I did it until the telescope was demolished.
By then, Conny had 21 years of data about the star. Over her Christmas break, she decided to analyze the data, just for fun.
You see, my work is my hobby. I just like what I do. That's the most pleasant thing to do, is analyze stars. I was analyzing that star after I knew for sure I will not get any more data with that telescope because the telescope closed down. So that was a good moment for me to say, okay, it's now or never for that star.
Conny sat in her upstairs living room and started crunching the data while her daughter colored downstairs.
And then all of a sudden, I saw the frequencies.
Not just one frequency, but 6, enough to figure out the internal rotation of the star. This had never been done before.
It was actually the first star beside the sun where we had a measurement of the internal rotation rate. That was a breakthrough in our field.
Conny couldn't believe it.
And I was shouting like, ah! Why didn't I see this before? Because it's so, once you have detected something, it's so obvious.
But downstairs, her daughter was unimpressed.
She asked what was going on. And then I tried to explain to her what I had found. And so then she was like, oh, so what, She was a 6-year-old. So what? Nerdy mother, having found something and working again in her holidays.
Her colleagues had a better reaction. Conny's research was published in the journal Science, and it provided a template for finding the internal rotation patterns of other stars.
We realized as a community, okay, we want to do this not for one star, but for hundreds of stars, because they all rotate differently, but you cannot do 100 times 20 years of waiting,
So Conny helped organize a massive data collection initiative
involving tens of astronomers around the Earth, sitting at a telescope in different observatories.
This worldwide project made it possible to avoid some of the gaps in data that naturally happen when you're observing a star on your own, when daylight or bad weather get in the way. More information speeds up the time it takes to decode it.
You can do the same research in about, not 20 years, but less than 2 years.
But the field took an even bigger step forward when those observations went from Earth to space. Missions like the Kepler Space Telescope made it possible to study stars you couldn't even see on land.
We had the methods in place. It was just a matter of getting more data. And then the Kepler mission gave us thousands and thousands of stars with such data.
Since then, work in astroseismology has exploded, and Conny is right in the center of it. She co-wrote the first textbook about the field with Don Kurtz and her Kavli Prize co-laureate, Jørgen Christensen Dalsgaard. She's also spent time nurturing the next generation of scientists.
If I count master, PhD students, and junior postdocs, I have supervised more than 100 of them, which is kind of a lot.
But her impact expands far beyond those immediate mentorships. For decades, she's led initiatives to recruit students with diverse backgrounds and bring more women into science.
For me, that's very important as a person, that I do bottom-up inclusion, that everybody gets a chance to contribute.
She says this drive for diversity probably comes from her own story, when the help of a supportive teacher changed her path from a seamstress to a scientist. Conny Aerts is a professor of astrophysics at KU Leuven in Belgium. This year, she shared the Kavli Prize in Astrophysics with Jørgen Christensen Dalsgaard and Roger Ulrich. The Kavli Prize honors scientists for breakthroughs in astrophysics, nanoscience, and neuroscience, transforming our understanding of the big, the small, and the complex. The Kavli Prize is a partnership among the Norwegian Academy of Science and Letters, the Norwegian Ministry of Education and Research, and the US-based Kavli Foundation. This work was produced by Scientific American Custom Media and made possible through the support of the Kavli Prize.